There's something I want to talk to you about that confused me for a long time. And I should say this up front. It's likely to confuse you too. You may have heard people say, quantum mechanics is strange, but it's nothing more than probability. Or you may have heard the opposite idea. It's mysterious. Human awareness actually shapes reality. Most people believe the real difficulty is the complicated math. To be honest, I believed that too at one time. But later, I realized something that completely changed how I saw it. The math isn't the real problem. The real problem is that nature simply does not match the pictures our everyday thinking tries to create. That's why I once said, very directly, I can safely say that no one truly understands quantum mechanics. If you stay with me, I'll explain exactly what I meant by that and why it isn't a failure. It's an open invitation. Let me start with a confession. I love understanding things. I don't mean memorizing words or repeating slogans. I mean that satisfying click when a bunch of confusing facts suddenly become one simple idea you can carry around in your head. When I was a young man learning physics, classical physics felt like that. Newton's laws, Maxwell's equations. Beautiful. You can picture them. You can imagine little balls, forces fields. Even if the pictures aren't perfect, they guide your intuition. But quantum mechanics doesn't just give you new facts. It attacks the very machinery you use to make sense of facts. It attacks your expectations about what an electron is, what it means to go somewhere, what it means to know something, what it means for an event to happen. And the strange thing is quantum mechanics works. It works better than any theory human beings have ever invented. It predicts things so accurately that you start to suspect the universe is playing a joke. Like it's saying, you wanted a neat picture. Too bad. Here are the answers anyway. Now, when I said nobody understands quantum mechanics, I didn't mean we can't use it. We can use it brilliantly. I used it myself to calculate all kinds of things about atoms and light and particles. We know how to get numbers out that match experiments. But understanding, real understanding, often means you can tell a story about what's really happening in a way that doesn't contradict itself when you push on it. In classical physics, you can do that. In quantum mechanics, every story you try to tell, every comfortable metaphor, eventually snaps. I once put it this way. On the other hand, I think I can safely say that nobody understands quantum mechanics. So do not take the lecture too seriously, feeling that you really have to understand in terms of some model what I am going to describe, but just relax and enjoy it. I am going to tell you what nature behaves like. That wasn't me giving up. That was me telling you the right strategy. Stop demanding the wrong kind of explanation. Because the trap is this: you want quantum mechanics to behave like something you already know. You want it to be a wave, or a particle, or a hidden clockwork, or a mind trick. And I'm telling you, person to person, if you insist on one of those pictures, you will either end up fooling yourself, or you will end up angry at the universe. Here's where it gets interesting. At Caltech, when I taught quantum mechanics, I could see this struggle in students' faces. Bright students! They could do the calculations. But then they'd ask the same question again and again in different costumes. But what is it really? And every time, I felt the temptation to give them a story that would make them feel good. But physics isn't about comforting stories. It's about what nature actually does. So I started leaning hard on one experiment, one simple setup, that contains the whole trouble. I even said it contains the only mystery of quantum mechanics. And if you follow me through that one experiment, You'll feel the exact point where understanding breaks and something deeper begins. Let me tell you what happened next. I want you to imagine a simple machine. You have a source that fires electrons, one at a time if you like, toward a wall with two thin slits in it. Behind that wall is a screen that lights up wherever an electron arrives. Now, you might be thinking the same thing I thought the first time. Okay, an electron is a little particle. It goes through slit A or slit B, hits the screen somewhere, and if I shoot many of them, I'll get two piles behind the slits. That's the classical guess. Perfectly reasonable. But that's not what happens. You shoot many electrons and you get an interference pattern, bright and dark bands like waves interfering, not two piles. A delicate stripe pattern that says, unmistakably, something wave-like is going on. So you say, fine. Electrons are waves. Then you turn the machine down so low you fire only one electron at a time. And now you're expecting. Okay? One electron is a little spread out wave. It should hit the screen as a little spread out smear. But that's not what happens either. Each electron arrives as a single dot, a localized hit one place, like a particle. So the electron behaves like a wave when many of them are sent, but each individual one arrives like a particle. Now here's the first place your intuition fails, because you might try to patch it up with a story. Maybe each electron goes through one slit, but the source wiggles or the air vibrates, and that makes patterns. No, the pattern builds up even when conditions are controlled. And it builds up from individual dots, like nature is patiently painting an interference pattern dot by dot. At this point I remember a particular feeling, almost irritation, because I could do the calculation. The math says, compute a probability amplitude for going through both slits, add them, square the magnitude. There's your pattern. It's straightforward. But my human brain kept muttering, yes, but how does the electron decide where to land? So I tried the obvious trick. What every curious monkey tries, I said. Let's catch it in the act. Let's put a detector at the slits and see which slit each electron goes through. And this is where I started to see the pattern. The moment you arrange things so you can tell which slit it went through. Even in principle, the interference pattern disappears. You get two piles, like particles again. And if you take the detector away, the interference returns. So your first impulse is to say something like, the act of measurement disturbs the electron. Sometimes that's true in a rough, practical sense. But if you stop there, you miss the deeper point. Because you can make clever detectors, weak detectors, indirect detectors, you can play games. The moral stays, the possibility of knowing which path destroys the interference. I couldn't believe what I was seeing, not because the experiments were sloppy, but because nature was acting like a thing that refuses to be categorized. But then something unexpected happened. In my own thinking, I realized the real pain wasn't waves and particles. The real pain was that I was trying to imagine the electron as having a definite story in between emission and detection. I wanted a movie in my head. In classical physics, you can do that. A rock arcs through the air whether you watch it or not. The path exists. Your ignorance is just ignorance. In quantum mechanics, the path is not merely unknown. The theory doesn't assign a single path at all. It assigns an amplitude, a complex number, to every alternative, and you add them. And I'll tell you something, when I started thinking this way, it became less mystical and more honest. The theory was not saying, here's what the electron is. It was saying, here's how to compute what you'll see when you do an experiment. Now, people love to argue about what this means. They'll tell you Copenhagen. Many worlds, pilot waves, hidden variables, consciousness, and so on. I've listened to these arguments, and I've had them myself. But I'm going to be careful here. The phrase, "shut up and calculate," is often pinned on me, but it's widely credited to David Merman, not me. Still, I understand why people associate that attitude with the way I talked. I was always suspicious of explanations that don't pay rent in predictions. Yet I also cared deeply about understanding, not in the sense of having a comforting picture, but in the sense of having a clean way to think without lying to myself. So I built a different mental habit, and it came partly from a different formulation of quantum mechanics I worked on. The path integral. You don't have to know the heavy mathematics for the key idea. The key idea is, if you want to know the probability of a particle going from here to there, you don't assume it takes one path. You consider all possible paths and add contributions from each, weighted by the action. That sounds crazy if you demand a literal story. All paths. Through the walls, around the universe. But as a calculation rule, it's magnificent. And it tells you something about the world that is very hard to say in ordinary language. The universe seems to compute outcomes by combining alternatives in a way that is not like classical ignorance. Here's a teaching moment I used to enjoy. I'd ask students, "What happens if I block one slit?" They'd say, "Then you get a single slit diffraction pattern." Right. And if both slits are open, you don't get pattern A plus pattern B. You get a new pattern with cross terms, interference between alternatives. That cross term is where the devil lives, because it means you cannot treat the two alternatives as separate classical possibilities that simply add. You must add amplitudes, not probabilities. And the interference term depends on relative phase, something you cannot represent with an ordinary probability story. I failed again and again to find a simple classical analogy that didn't break. And every failed analogy taught me something. The problem is not that quantum mechanics is complicated. The problem is that the classical categories we evolved with, little objects with definite properties, are not the right categories at atomic scales. This is where my understanding completely shifted. I asked myself a question that sounds innocent, but it's poisonous. If the electron doesn't have a definite path, what does it have? And the answer, at least the honest answer, is it has a quantum state, a wave function, an amplitude distribution. But the wave function isn't a little physical jelly spread in space the way you picture water waves. It's a mathematical object that tells you how to compute probabilities for different measurement outcomes. Now you might say, fine, so it's just information. But then I ask, information about what? And you find yourself sliding around on a slippery floor, because every time you try to say what the wave function is about, you end up smuggling in classical notions like the electron really is at some unknown place, but the interference pattern says no. Then you try another line, maybe the electron is in both places at once. That's a phrase people like, but it's dangerous, because it makes you imagine a ghostly electron literally split into two halves going through each slit. But then when you detect it, it snaps into one dot, so you invent a collapse. But collapse is not a mechanical process described by the Schrödinger equation. It's an update rule for your predictions when you incorporate an outcome. It's the theory's way of keeping you from predicting interference after you've obtained which path information. Now here's what changed everything for me. How I tried to explain, nobody understands. In ordinary life, we think understanding means you can track a story in space and time. You can say the thing was here, then it moved there, and it always had its properties. Quantum mechanics refuses that. It says your description is tied to what you can actually set up and observe. Not because you're weak, not because you're stupid, but because nature is built that way. And I noticed something else, which I used to press on students in quantum mechanics. Questions are physical interventions. Asking which slit is not just asking politely. It requires building an apparatus that makes which slit a well-defined outcome. And the world responds differently when you do that. So the question, what does the electron do when nobody is looking, is not just unanswered. It may be ill posed in the same way. What is north of the North Pole is ill posed. Not because it's forbidden to ask, but because the language assumes a structure that doesn't apply. At this point, I would sometimes dramatize it on the blackboard. I'd draw two slits. I'd draw a detector at one slit. And I'd say, if you can tell the path, you don't get interference. If you can't tell the path, you do. Then I'd look at the class and say, now, do you like it? Because liking it has nothing to do with it. Nature doesn't care what pictures you prefer. And the turning point is accepting this. Quantum mechanics is not a description of things doing things the way your intuition expects. It's a new kind of rule about correlations between preparations and outcomes. Everything I thought I knew was about to change. Again, because even after you accept the double-slit mystery, you still might think, okay, fine. The electron is quantum, but surely reality itself is still made of things with definite properties. Quantum mechanics is just a strange filter between us and reality. Then you learn about entanglement. And now the trouble is no longer, where did the electron go? The trouble is, what does it mean for two separated systems to have properties at all? I used to imagine this. You take two particles and prepare them in a joint state so that certain measurements match perfectly. Then you separate them, far apart. Now you measure one, and instantly you can predict something about the other. The old classical instinct says, they had those properties all along. But quantum mechanics says the joint state is not just a statement of ignorance. It's a statement of what outcomes are even possible and how they correlate. The properties are not assigned individually until you choose a measurement context. And if you try to insist on a classical hidden story, you run into very hard theorems and very clever experiments, Bell's inequalities and their violation, that suggest the classical notion of local hidden variables can't reproduce all quantum predictions. Now, I'm not trying to drown you in foundations. I'm telling you why the phrase, nobody understands, has teeth. Because the confusion isn't a minor detail. It's the center. The structure of the theory is telling you, your old categories are not the categories of the world. At this point, a lot of people try to escape by choosing an interpretation like a religion. Many worlds, Copenhagen, Bohmian trajectories. These can be useful ways to think, but notice what happens. Each interpretation buys you a picture at a price. It either adds invisible structure, or it multiplies realities, or it changes what you mean by measurement. And I want to be honest about what I concluded. None of these pictures has become the universally accepted, frictionless story of what's happening, the way Newton's laws feel. That's the sense in which nobody understands. But, and this is crucial, the inability to settle on one story does not mean the theory is empty. It means nature is deeper than our storytelling instincts. This is the last loop before the climax. What if the real misunderstanding is our definition of understanding? And then it hit me when I said, nobody understands quantum mechanics. I wasn't bragging about how mysterious it is. I was warning you about a specific mental mistake, the mistake of demanding that quantum mechanics fit into the same kind of mental model you use for everyday objects. Because our everyday understanding is built from evolutionary convenience. We grew up throwing stones, catching balls, walking through doors. We didn't evolve to add complex probability amplitudes. We didn't evolve to handle interference of alternatives. So quantum mechanics shocks us not because it's irrational, but because it is rational in a new way. Here's the best metaphor I can give you from my own experience as a teacher. You can teach a child that the earth is a sphere. The child can repeat it, but the child still feels like the world is flat. The feeling comes from a local approximation. Quantum mechanics is like that, but worse, because classical intuition is not merely an approximation in the same picture. It's a different picture altogether. Quantum mechanics doesn't say, your picture is almost right, just add a correction. It says, your picture breaks at the seams. Use this rule instead. So the honest form of understanding is not a single story of what the electron really did. The honest form of understanding is to know which questions are meaningful, which experiments define which outcomes, and how the amplitudes combine to give you the statistics you observe. And if you can do that, if you can predict what happens when you open two slits, close one, add a detector, remove it, then you understand quantum mechanics in the only sense nature is offering you. That's why I told people to relax and enjoy it, because the reward is enormous. You get to see nature's behavior directly, without insisting that it flatter your intuition. This changed how I see reality. I used to think the goal of physics was to find the one perfect picture behind everything. A little machine in the sky that, if only we could see it, would make the universe feel familiar. Now I think the goal is stranger and more beautiful, to discover rules so precise that they force us to expand what we mean by picture, what we mean by event, what we mean by our explanation. Quantum mechanics still amazes me because it is humbling. It tells me that my imagination, powerful as it feels, is not the judge of reality. Reality is the judge. And yet, we can participate. We can ask questions in the form of experiments. We can compute amplitudes. We can build devices that work, lasers, transistors, MRI machines, all because we learn to accept a rule that doesn't match our instincts. So when you hear me say, nobody understands quantum mechanics, don't hear despair, hear honesty, and hear a challenge. Stop trying to force the universe into a story you already know. Let it teach you a new one, because this willingness to be shocked and to keep going anyway is the beauty of physics, and I wanted you to experience it with me.